Let's start. Hi, everyone. Welcome to XCamp 2023 March USACO Solution Discussion. My name is Charlie. I'm the co-founder and the principal of XCamp. Today, we will like to discuss a quick introduction on XCamp. Then our instructors will discuss the US contest. Yeah, we will start with the bronze first. Then we will discuss the 2022 and the 2023 this past season, the trend of the USACO contest. Also, we will show you how to prepare the next USACO in 8 months. Finally, we'll have time for the Q&A. Some of you might know XCamp is a Silicon Valley-based coding academy. We have classes open nationwide online. We might have on-site class from the summer or fall. We have the class from beginner to the master level. Master level, I means the IOI, International Olympiad of Informatics level. Also, we have our curriculum developed by our world level top contestants. We have proven record, so we help students to have solid knowledge on data structure and algorithms. Also, we already have 4 USACO campers in the last season. Hopefully, we have more in this coming season. We have 3 students from the master class among the top 10 in the past 3 contests this year. Also, we have 6 students joined Platinum in the past 3 contests too. Today, we have the Alex Du, who will help us to illustrate the problems on USACO. So let me resume this recording here. Alex Du, he was an ex-camp student from the beginner level and reached the USACO Platinum Division. For the others, we have Albert for the silver level falling, and we have Arvin on the gold level. Without further ado, I would like to turn this to Alex Du.
Okay, so on just like basically the trend of USACO bronze this year. So open this year was like exceptionally hard, so it's kind of like an exception, like not a rule. So there's not too much to talk about. I think like all 3 questions on open were like really difficult, and the cutoff on open is probably gonna be really low. But in general, like the other contests this year, they were like harder than the ones from last year in general, but they weren't like too much harder. In general, they had a trend where it was like one of the questions was usually really easy. The other one was like medium difficulty. It's like usually solvable for people with like bronze level like knowledge. And then the last one is like there's usually a third question that's like really hard, but like you can usually get like some subtasks on it. Yeah, so in general, the contest strategy for like all these contests was like find the 2 easy questions. It wasn't usually in order a lot of times. Like the first question sometimes was like really hard, or like yeah, and like the third question wasn't always the hard one. And so you just had to read all the questions, go through them, like just go through all of them first, pick out the easy ones, and then from there, just try to solve the 2 easier ones and then get subtests on the third one. And a lot of times that gave you enough points to reach the cutoff to pass. Yeah, that's basically actually in terms of like material covered in bronze this year, it was mostly like observation problems. Like the easy problems were just brute force, like normal. Yeah, you just had to like look at it, just brute force it. The harder ones were usually of like observation, or like basically just greedy problems where you had to like make a observation first and then look for one. I remember like one question that was actually like a bit set question. And I feel like that was the one that required like the not bit just like bit mask question, and that was the one that required the most knowledge. But other than that, there wasn't too much. Okay, so should I just go over the bronze problems now? Charlie?
Yes, please go ahead. Yeah, you can
Okay.
share your screen now.
All right, so now I'll just go over the questions from the bronze contest. I'm going to be going over them like the order, like for like first question 1, then question 3, then question 2, because I think question 2 was the hardest one in this contest. Okay, so problem 1, I'm gonna assume like everyone's like read the question, but I'll also just go over the general like details of the question. So just like problem 1. Let me see. Okay, so there's n letters, n less than equal to 10 to the 5th, 2 times 10 to the 5th, but doesn't matter. And then so letters are either E, B, E, or F. And then F can turn into either B or E. Find all possible number of like BB or EE substrings. So that's the general just problem statement. So now if we just approach this problem, like when we look at this problem, we can see that like the letters we care about is just the F's, right? Because those are the only ones that can change the number of BB and EE ones total. Like we can just count the initial BB and EE ones that are initially in the substring without F's, and then just add that to the final, like all of our final answers. So that doesn't really change much because those are all like constant and like don't change regardless of the choices of F. So now like we just have to only care about F's. And another observation we can just immediately make is that like we can just we just go through the F's like in terms of substrings of F. So if there's like a bunch of F's in a row, we have to like process them all together because they all build off each other. So like process substrings of F's. Right, because we can't process them like one by one because otherwise it'd take way too long. Like we can't just like choose like either like B or E for each one because that's like 2 to the power of n. So we have to just process substrings of S because they all build off each other. So next, so if we like see each substring, we can see that they're either like sandwiched between like there's only 4 possible combinations of things they're sandwiched between, and out of like the 4, they're all like kind of similar. So it'll look something like this. It'll be like B, maybe a B, and then like there'll be like a long substring of like all F's, like F, like, and then there could be like another B or something, or another letter. And there's only 4 possible like combinations of letters like before and after. It could be like either BB, BE, EB, EE, or EB. And out of these, so we can see like it doesn't actually matter whether it's a B or an E. All that matters is like whether they're the same or different, right? So the only 2 combinations is actually like either like BB, EE, or BE, EB. Like these two are like both the same. Like each of these 2 are like the same within themselves. There's only 2 categories, so either they're same or different. So now we just have to do some casework to like find exactly how many how many different possible numbers of like the BB or EE substrings we can make for each of these like combinations. So if, like our first thing is like, so if they're the same, so first like case 1, like same. Actually, I'll do them side by side. Let me just erase this real quick. So there's 2 cases here. So either what the letters before and after the substring is the same or different. So case 1, same. Case 2, different. And then we list out like, so how many F's, number of F's in between. F's between. between. So if it's 1, that means like we can see that like the case looks like it's like B, F, B, and then or like B. And for this, there could just like it's either 0 or 2. We can just see this because if we choose like B for this F, it would be 2. If we choose E for this F, it'd be 0. And then for the 1 case, for different, it'd be like B, F, E. And then this would be either, we can see it's just 1. There's only 1 choice. No, regardless if you choose B or E, you'll get 1 for the answer. Now for case 2, we can see that it will look basically like B and then like F, F, and then well, F basically can be like considered like a blank space because you can choose like either E or B to be put in between. So it'd be like B, blank, blank, and then like another B. So we can see that whether you choose like E or just like 2 choices here for the first letter, we can choose like B to begin with, or we can choose like E here. There's 4 possible choices total. But if we just do the casework, we can see that there's like, for example, this case would have 1. There's also another case like we can also get 3 out of it. And if we just consider all the cases, we can see that it's basically impossible to get any other cases. And then for if it's different, it would be like B, blank, blank, E. And then just doing the casework again, we can see that it's pretty easy to get 0. It'd be like B, E, B, E, so it'd be 0 here. And but we can also get 2 out of this just by doing this. And there's no other way to get more. So next, move on to the next case. It would be 3 in between. So it would look like this. At this point, like we need to like notice that like in order to like simplify our calculations here, a cool way to do it is like we can just either pick B or E for the first one, and we can see that it turns like the remaining substring turns into something we've already calculated. So if we choose B for the first one, we add 1 to the count, and then it turns into this subcase. So it would be just 2 and 4. It would be 2 and 4. And then if we choose E for this subcase, like E for here, it would turn into this case right here. So we need the total number would be 0, 2 coming from this side, and then 2 and 4 coming from that case. So it would be total would be like the combination of 2. So it could be either 0, 2, or 4. And then going on, like same logic for this, it'd be like B space, 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 E. And we see that if we choose B for this first one, it'd be like 1 plus all the results from here. So it'd be like 1 plus the results from here. So we'd get 1, 3 from these 2. But if we choose E for this one, it would be the same as the one. It would be the same as like the ones here, because it'd be like 2 ones, 2 like endpoints are the same, and then 2 blank spaces in between. So it'd be 1, 3 for these ones as well. Yeah, if we just keep going on and just doing the math for all of these, we can quickly see that basically we like notice a pattern emerging here. It's just like for like the ones with even parity, for case 1, it's like 0, 2, and then it's like 1, 3, and then like basically it's just counting either even or odd numbers. Just like if we just do all the casework and like bash it all out. And like this, we can see like why this casework emerges, because like using the same reasons as before, like we're basically just building off of previous cases, right? So for this case, we're just picking, if we pick B here, then it's just 1 plus everything in the previous case here. And over here, it'd be like if there's 4 spaces here. If we pick B here, it's just building off the cases over here. And then 1 plus all the cases here, plus the 0, because we can also build off the cases here. Actually, yeah, we just directly build off the cases here, actually, because it's just, if we just pick E for this case, we're just directly using all the cases from this side. So it's just 0, 2, 4. That means that this pattern of just all even or all odd numbers will will remain for every single possible combination. So all we have to do is just consider the parities of like the letters before and after each substring of F and the number of Fs in between, and we can just find like the number of different substrings, like possible numbers of substrings of EB or EE. And using this knowledge, now that we know that like the amount we're adding for each substring of Fs is either like a chain of even numbers like 2, 4, 6, 8, so on, or a chain of odd numbers 1, 3, 5, 7, so on. We can quickly like see how we can get like the final combination of like the number of numbers. Basically, let me just clear this real quick. So numbers we're adding is either like 2, 4, 6, or like 1, 3, 5, 7, ... Each time, if we're adding like, if we can either add 2, 4, 0, 2, or 4, our answer is always just a continuous sequence of numbers separated by 2, because every single time we're only adding like 2 numbers at a time. So for example, if our first like choice was like 0 or 2, then that means that like our current answer is either 0 to 2. And if we were to add like another 0 or 2, that means that our answer turns into 0 to 4. And we can see that like no matter like what even or odd we add, since all the things we're adding are always separated by 2, the final like string of like answers we can use is always like just numbers separated by 2. And the like we can also see that like if we have 2 choices here, the number of answers we can get grows by 1. And like if we're able to add like 0 to 4 to like 0 or 2 instead, then our answer choices become 0 to 4, 6. And like basically the string grows by 2. So the solution is just basically we see like how many numbers we have to choose from each segment of F. So if we call like let me just pick a random, like A, the number of variables, the number of numbers we can choose from each segment, that means that our like the number of possible answers we have grows by A minus 1, because it's just like we can either add 0 or we can add we add 0 to like keep everything the same, and add 2 and 4 at the end to grow the sequence by that much, which is A minus 1. This applies the same for like odd numbers. If it's odd numbers, we just have to add 1 to the beginning of the sequence to like everything. So if we add 1, 3, 5 instead to 0 or 2, then our final sequence becomes 1, 3, 5, 7. So it grows by length too, but we also have to add 1 to everything, to every number in the sequence. If we add like another 1, 3, 5, then the sequence becomes 2, 4, 6, 8, 10, 12. It grows by 2, but we also add 1 to everything in the sequence. So we just keep doing that. After we calculate the number of possibilities for every single subsequence of F, then we can just use this property to just like loop through the whole list and just grow the numbers like this. Does anyone have any questions on how to do this? Okay. If no one has any questions, then we can go on to problem 3. So for just a quick refresher on the problem statement, there's basically n cows, n less than or equal to 2 times 10 to the 5th cows. And then they just do this sort of dance where there's like there's a sequence of sequence K of K numbers less than or equal to n numbers. Just labeled A1, A2, A3, ... AK. And then in at each moment of time, A1 goes to A2. The cow at position A1 goes to A2, A2 goes to A3, and then so on, with AK going to A1. So the cows all just like shift in a circle like this. Let me make sure I'll specify it's like this. So it's like a circle, and they'll just loop back on itself. And then as well as this, at each moment of time, A1 becomes like A1 minus A1 plus 1, A2 becomes A2 plus 2, A2 plus 1, I mean, and then A3 equals A3 plus 1, and then so on. So basically the entire circle of like the cows shifting also shifts over by 1. Now, because like, and then we want to like see that after like t moments of time with t less than or equal to 10 to the 9th, where all the cows are. Okay. Does everyone understand the problem statement? If anyone has questions, just ask, because I'm gonna delete this to explain to them. Okay. All right. So now for the solution. So the first observation we can make is that like after the cows are shifted over, like the cow from A1 from position A1 gets shifted to A2. But then like, and then the cycle also shifts over. But like the only cow that's able, the only like, even when the cycle's shifting, the only like a value that each cow can get shifted by remains the same. Because basically like once a cow, like A1 to A2 could be like, I don't know, let's just say like A2 equals A1 plus 3. So the cow in this, like in this position, in like position 1, gets shifted to position 4. So like if A1 is 1 initially, A2 is 4 initially, it's like that. But then like as the A values increase, so it would be like 2, they'll become like just move this below. So if initially like the A values are like 1, 4, and then becomes like 2, 5, and then 3, 6, and then it'll become 4, 7. But like in between this, there's no part, like this is still A1 and this is still A2. So eventually, like the cow that was initially at A1 will have A1 catch up to it after it gets pushed to A4. And because there's nothing in between A1 and A2, there's no other A value that like that one cow gets shifted by. Like that's the key observation here. So key observation, even as everything shifts, each cow only gets pushed by one A value. Right. Yeah, and the reason for this is that because like it goes from one A value to the next, with that A value being larger than the previous one, and there's no A value in between either one. So as A can only increase, there's no other A value that will like that can reach that cow. So this makes the problem like a lot easier because we can see that it's just counting the number of times that each cow gets pushed by the same A value, right? Because each A value, like the difference between A values remains constant, even though like no matter the shift. Like going from A1 to A2, like if it's +3, it still remains +3 every time, even if A1 and A2 gets shifted, right? If it's like 1 to 4, it's just like a difference of 3 between them. If it's like if it's 2 to 5, still a difference of 3, 3 to 6, still a difference of 3. It's just +3 every time. And then like, so eventually like if it gets pushed to 4 to begin with, after 3 minutes, the A values will catch up to the cow again, and it will get pushed from 4 to 7. So this means that we can see that all we need to do is just check for each cow, like how many times, which A value gets pushed by, and then how many times it gets pushed. And then that will give us our final answer. So as for how to do this, it's just basically a bit of math. So we first, like for each cow, find which A value pushes it. And the reason for this is I mean like the A value that pushes it is just the first A value that's less than it. Less than it. Let's just call it AI. Call it AI. So if like first push occurs like time, it's just initial position, like let's just call the cow like CI. Well actually, yeah, a time like, well actually we don't call it CI, we can just call it like X. At time X minus AI, because that's how long it takes for AI to rotate into X, and then for X to be pushed over to the next one. And then it gets pushed AI plus 1 minus AI every time. And then so the number of times this happens is basically the number of times that AI gets shifted into it. So let's just call this like this value. Let's just call this like D. So all I'm going to do is just like find the remaining time, like remaining time divided by D. That's how many times it gets pushed, and then multiplied by D. Well, this basically is just this is like a floor. It's like this like floors it, and that's how many times that this cow gets pushed. And then times D is like how much each push is. So this is how much the cow moves like total, like throughout all the entire time. And then to find the final position, we just do like this value like value modded by like the circle, number of cows in the circle, which is N in this case, to find exactly where each cow, like where the cow is in the end, because this is like not considering the fact that it loops back on itself. Does anyone have questions for this problem? Okay. If not, we'll just go on to question 2, which is probably the hardest question on this contest. Okay. All right. Problem 2's problem seems like kind of complicated. So basically, there's two types of sentence. Like Farmer John just like wants to make a bunch of sentences, and sentences are of two types. So type 1. Actually, well, I mean, first, like let's go into like, so there's 4 types of words. 4 words. It's either noun, intransitive word. I'm just gonna like abbreviate them. So like it'll be a transitive verb, so T verb, IT verb, or intransitive verb, or a conjunction. And then 2 sentences that you could also make. So type 1, noun plus IT verb. Type 2 is noun plus T verb plus like possibly a lot of nouns, but it'll be like noun and then like possibly like comma noun and then like comma noun, like as many as you want here. Doesn't really matter. And then can join, like we can join 2 sentences together with one conjunction, but then like after that it can't be joined again. So can join 2 sentences with conjunction. Yeah, like once. That's basically the general rules of the problem, and we want to like maximize the total number of words we use like in complete sentences. Total number of words. Okay. Does anyone have questions about the problem statement? All right. If no one does, I'm just going to erase the problem statement so I have more space for the explanation. Okay, now onto the explanation. We can see that basically immediately nouns and periods are going to be our limiting factors. And periods are our limiting factors. Well, not exactly periods, like it's more like the number of sentences, right? Like because we like everything, like every single sentence requires some nouns and then also like a period at the end or like a conjunction and then a period. So those are like the 2 things we need to keep track of. So first off, okay, we can just immediately get rid of conjunctions by just like saying, so number of sentences total is periods plus conjunctions. Well, it's like minimum of periods plus conjunctions, minimum periods and conjunctions. And this is because yeah, like every single sentence either needs a period, or it can be like a conjunction and a period. So conjunction can basically just add another sentence to our total count. Yeah, so and this basically just gets rid of like conjunctions, because we can just treat them all as like periods or like number of sentences. So now we go into all the casework. There's like a lot of casework in this problem. So first casework, so if the number of nouns is less than the number of periods, and less than the number of sentences, I mean, then we want to prioritize sentences of type 1, because sentences of type 1 require one noun for each verb. Will give us one noun for each sentence, while sentences of type 2 give us like have to take like 2 nouns per sentence. And we want to maximize the number of sentences in this case because we don't have enough sentences. Actually, when the number of nouns is, yeah, we want to maximize the number of like of like sentences, because we want to use as many verbs per noun, because we're short on nouns. So prioritize sentence of type 1, because it's like a more efficient way to use our nouns, because we don't have enough of them. But if we do have enough nouns, so if number of nouns is greater than the number of sentences, this means that like we have enough nouns and we instead want to like prioritize being able to use all the nouns up. So this means that like we want to like use sentences of type 2 to use up all our nouns. Use up nouns. So let's just say a variable, like call D equals to number of nouns minus number of sentences. So we want to like use we only use like type T verbs, sensitive type 2, to use up nouns, but we also don't want to use too many of them, like just in case like we don't actually have that many nouns, and we still want to use sentences like of type 1 to like finish it off, and like make sure we are using up like all of our sentence count as well. So we basically just use like prioritize type 2 sentences, 2 sentences until we use D of them. But sometimes like we don't have enough, like just some things we're short on. Like for example, if D is too large, there might be like not enough either total sentences or not enough like IT verbs, intransitive verbs. So then just like that goes into like some more casework. So if there's not enough, like at that point, then we also want to start using our commas then. So if not enough sentences or IT verbs, we start using, because like we just want to like try to use as many nouns as possible in this case. We want to use them all up, because that's just how we got like all the words used, using commas to add verbs. So after we do all this, like if we like use up either enough nouns or we like just run out of everything, we run out of commas, we run out of IT verbs, we run out of like after this, after using everything up or using enough nouns, we go back to type 1 sentences. And the reason for this is type 1 sentences, like if we have enough nouns and sentences, type 1 sentences are more efficient, because they like efficiently use like 1 noun per sentence, while type 2 sentences can use like way more. So after we like burn through all our extra nouns, we just want to go back to type 1 sentences to like finish off and use up the remaining nouns. Now, like after we have all this, like we're still in like, there's still like a big part of the problem, which is just like implementation. It's just like, after you choose exactly which sentences to use, you're going to have to like yeah, just do a lot of like bashing to like print out exactly like what you need. You have to choose the proper like nouns, like verbs, yeah, and all that. But that's just like implementation and just like not too much logic in there. But yeah, that'll also take a good amount of time. Does anyone have any questions about this problem? This problem was like a lot more complicated. If anyone's questions, just like ask. Okay. I'm gonna assume there's not many questions. So there's not many questions. I'll just like go into a quick like contest recap, I guess, for like strategy of this contest. There's not just like yeah, again, like it's important to like read all the questions first because if you didn't, like problem 2 was probably like the hardest like and most time consuming problem in this contest. Like the casework itself isn't like the casework itself is pretty bad, but like even after you have all this logic down, it'll still probably take you like half an hour to an hour just to code this at least because there's just so much like bashing and other things that you need to make sure. So for this problem 1 wasn't like the worst. Like problem was like doable if you as long as you like are able to see like the casework and like figure that out. The implementation for problem 1 wasn't too bad. Like problem 3 was you had to like make the observation, which wasn't too easy, but like if you make the observation, the problem becomes pretty easy because it's just math and it's really quick to implement. So problem 1 and 3 were like the easier ones in this contest, and the ones that are probably solvable. Problem 2 was like, yeah, it's pretty challenging, and honestly, it's like kind of hard to get like to even get subtasks on this because it just requires a lot of bashing. But like if you have enough time left at the end of the contest, you probably could have gotten like some subtasks, which is with like casework and just like trying out different things. And honestly, on this contest, like I'm expecting like the cutoff to be like really low. It'll probably be like 700 at highest because I think this contest is pretty hard. Yeah, like all three of these problems were just like ad hoc problems, really. Third one was like greedy to an extent with like some observation, but problems 1 and 2 were just like casework. You just had to like bash through all the cases manually. It wasn't a really smart solution that I saw. Yeah, so if anyone has more questions, just ask in the chat. I'll wait for a bit, but otherwise we'll just continue moving on. Okay, I don't see any response in the chat, so I'll just stop sharing and give the screen to teacher Charlie.
Yes. Thank you, Alex. Let's continue our discussion here. You discussed the trend. Maybe you can. I think you can share that again here. Let me share my screen. Can you see my screen? Alex, you are on mute.
Oh, sorry. Yeah, I can see your screen.
Yeah. Okay. Yeah, I think you discussed the trend. How about if maybe you repeat that? I think that's important for the.
Okay. Yeah. In general, for the trends of this contest, I think like open wasn't really like open didn't really follow the trends of this year. Open was just like really hard. Like it kind of did, as in like for like the general trend of this year was just one easier problem, one medium problem, and then one like hard problem. Like I think the strategy in general for bronze was just you had to go like find the 2 easy problems and just like make sure to solve them. They're not always in order, so they're not always the first and second questions. So just make sure to read all the questions first. And then yeah, so it's just mainly just get full points on the 2 easier problems and try to go for subtasks on the third one. If you have like enough time and like ability to solve the third question, and you can like just full solve the contest, that's good. But like otherwise, a lot of times subtasks on the third questions was enough. Open like this year kind of followed this trend with like two somewhat, but like I think just in general, Open this year was just had like 3 questions that are like a lot harder than every other contest. So yeah, the cutoffs are gonna be low, but in general, like for Open, if you could solve like you probably had to like skip 2. Solve maybe you can solve 1 and 3 and then go for subtests on 2, and that'll probably just get you like a pass. Okay. Well, this was the last USACO contest of this year, but in general, there's still like always next year if you didn't manage to pass this year. So next year, like XCamp offers like a lot of really great courses or to help prepare for questions, like especially those on like this US Open, where it's just like a lot more tricky and just like, coding intensive questions. So for our first, like the first XCamp class is basically a weekly online class, which covers general knowledge and like of algorithms and other things. They run through the spring, summer, and fall quarters. And overall, just like our like 10-week online courses that offer just like a lot of like good knowledge on algorithms. So the second type is just a lot of times problems just require like a lot of practice, especially like the ones on this US Open contest, just require like observation, casework, and just general coding. There's going to be like mock test classes for all levels from October to March. They provide just a lot of problems and a lot of training to help you work on like various problem solving abilities. And the third type of class is just intensive training classes during the summer and eventually also the winter, but that will do later. They offer like classes from bronze all the way to plat. There's limited spots, and it's just like basically a week, 2 week long, or like 1 week long intensive like course for. It's just like the entire day of just problem solving, learning new algorithms, and just all around like you get to like hang out with friends and learn a lot about coding and improve. Yeah. If anyone has questions or wants to contact XCamp, just either like ask now or like use any of the contacts listed on the screen.
Thank you, Alex. Also, students, yeah, congratulations. You finished another USACO season. I hope some of you passed USACO bronze. If not, just keep up. I think the learning experience is more important than just reaching a goal. Okay, thank you all. Have a good night.